and welcome to Simple Harmonic Motion, a video documentary. The objective of this experiment is to find the spring constant of a spring by measuring the period of the mass spring system.
Materials we used in part 1 were video camera, motion sensor, data collection system, SparkView, laptop, mass set, spring, C-clamp, and other clamps. In part 2, we used all the same materials. In addition, added the meter stick, paper slips, paper, tape, scissors, and the rubber bands.
In part 1, the methods we used were 1. Gather all materials. 2. Set up ring stand and attach the clamp near the top half of the pole. 3. Attach the force sensor to the clamp. 4. Connect data collection system, force sensor, and laptop. 5. Attach the spring onto the force sensor. 6. Zero the force sensor. 7. Attach a 200-gram mass onto the spring and allow it to oscillate freely. 8. Record data from the force sensor on the laptop and enter it into data table A. 9. Repeat steps 6 through 8 with 100, 300, 400, and 500 gram masses, and to remember to zero each time.
2 were step 1, gather all materials. 2. Set up ring stand and attach the clamp near the top half of the pole. 3. Create 2 paper markers by cutting 2 horizontal slips of paper, folding each one around the meter stick, and securing each one with tape.
4. Secure the meter stick to the pole with 1 rubber band wrapped around the bottom and 1 rubber band wrapped around the top.
5. Attach the force sensor to the clamp. 6. Connect the data collection system, force sensor, and laptop. 7. Attach the spring onto the force sensor. 8. Zero the force sensor. 9. Measure the length of the spring and record in data table B. Attach a 200-gram mass onto the spring. Allow it to fall freely to its maximum amplitude. Stop the spring from oscillating and allow it to hang on its maximum displacement.
11. Record the force shown on the force sensor in data table B. 12. Measure the length of the spring extension from the top to the bottom of the spring and record on data table B. 13. Repeat steps 10 through 12 with 100, 300, 400, and 500 gram masses, and remember to zero the force sensor before each measurement.
We allowed the spring to oscillate freely for about 6 or so seconds and let the motion sensor record the heights of the spring as it oscillated. We then looked at the data chart that showed the position of the spring over time intervals of 0.1 seconds and attempted to find the 2 data points in which the mass was at the same height. Once we found these 2 data points, we subtracted the earlier time from the later time to determine the period. We repeated this for every mass.
The equation is force equals negative kx, where k is the spring constant. For the force 0.99 N, which is 100 grams, the extension of the spring is negative 0.0252 meters times negative k. So then you would divide 0.99 divided by negative 0.0252, which is equal to negative k. So the negatives cancel, and then your k is 39.29.
Percent error. You take the spring constant that you got for method 1, subtract the spring constant for method 2, and divide it over the spring constant of method 1, and take the absolute value. The spring constant we calculated for method 1 was 32.33 by finding the averages. The spring constant for method 2 was 33.33 by taking the slope when we graphed our data and dividing it by 32.33. Our percent error was 3.09%.
In performing this laboratory experiment, we aimed to determine the spring constant of a spring using two different methods. The first method we used was to use simple harmonic motion to determine the period of the mass spring system, and using a formula that describes the relationship between the period and spring constant to determine the spring
To
constant.
measure the period of each oscillating mass, we discovered that as the mass increased, the period increased. This is supported by the equation k equals 4 pi times the mass divided by the period squared. Since the spring constant must remain constant, the period must increase as the mass increases.
Determine the average spring constant of the 5 trials to be 32.33. The second method we used was to find the spring constant directly by measuring the distance by which the spring extended and the force of the mass on the spring, and using Hooke's law to calculate the spring constant.
As we added on weights to the spring to collect the data, we noticed that every time an additional 10 grams was added on, the spring extended roughly the same distance. This indicated that the distance the spring stretched by was directly proportional to the force applied to it, and there was indeed a constant by which the spring stretched by, a concept illustrated by Hooke's
We
law.
determined the spring constant to be 33.33 by graphing the data and determining the slope. The percent error between the two values was
This is
3.09%.
not part of the equation. T equals 2 pi. This quantity is the square root of m over k. Amplitude does not affect the period of oscillation.